and welcome to this live lecture. So I hope that everyone can hear me and see me all right. I'm trying to look at the chat during the lecture, so feel free to ask questions. And also I will be using this item pool website, so you can go to itempool.com/Kepler/live and ask submit your answers. There will be several of these quizzes. So the first one, just sort of a warm-up question asking what is your most favorite Platonic solid. It seems that we have a clear winner, but we won't know until I reveal the answers. So I will do that in a minute. Let me just quickly look at the chat. So VK asks, is this aimed at A-level students? And the answer is yes. So basically it's aimed at people at the end of their sort of high school years. I would say anyone aged 16 and above should be able to follow what I'm saying, and it is aimed to be an elementary derivation of the Kepler's laws. So we'll see how that goes. So let me perhaps finish this poll and reveal the answer. Well, there's no answer, there's no correct answer, but reveal what you have voted for. So most people seem to have liked the icosahedron the most. And in fact, I also voted, and I voted for icosahedron, so it's good to see that is people's favorite. But also dodecahedron got 3 votes, tetrahedron and octahedron got 2 votes each, and the set cube ended up last with only 1 vote. Well, at least the cube got 1 vote as well, so that's great. So as I said, this lecture is about the Kepler laws of planetary motion. And my aim is to show you how Newton's F = ma and the universal law of gravitation can be used to derive Kepler's laws. So that's the plan, at least. We'll see how it goes. So let me go to the first slide. So this is the story I wanted to begin with, and this is why I asked you about Platonic solids. So Johannes Kepler, the German astronomer, mathematician, had this idea at the end of the 16th century that well, at the time there were 6 planets known in the solar system, and he had this idea that maybe the 6 planets, the number 6, has to do with the fact that there are only 5 Platonic solids. And he had this idea that these solids, the planets should have their orbits as sort of spheres, and they would be spaced so that these Platonic solids nested within each other could give a structure to these spheres and a correct spacing so that the planets would keep their distance from one another according to these Platonic solids. So this is a great idea. This is a fantastic idea to have. And in fact, what Kepler imagined is that you take the orbit of Saturn, let's say, that's a sphere. That's what he imagined it to be, and you draw a cube inside of that sphere, just so it fits in the sphere that is the orbit of Saturn. And within that cube, you would draw another sphere that fits just right into that cube, and that would give you the orbit of Jupiter. And then you would take the sphere of Jupiter, the orbit of Jupiter, you would draw a tetrahedron inside of it, just so it fits. So an inscribed tetrahedron. And within that, you would draw another sphere, and that would give you the orbit of Mars, and so on with dodecahedron, icosahedron, and the octahedron at last. So this sort of idea, this structure, would give you ratios between the orbits of the planets, like so. So we see numbers like 1/√3. We see the golden ratio appearing. So it's all very exact and precise. The only problem is that it's wrong. So this is something that even Kepler realized, that if you fix the position of the sun, and let's say you fix the orbit, the distance of Saturn, and then you draw these distances given by the ratios that I just showed you, you will get the planets placed, the orbits of the planets placed like so, the distance from the sun, as in this bottom row, but the actual orbits and the actual planets are of a distances like so from the sun. So you can see that there are like big errors in this sort of in these distances. So it's inaccurate as a model of the solar system. So this is something that Kepler knew about, and he kind of discarded the idea, but even late in his life, he went back to it and sort of thought that it was he liked the idea so much so that even though he probably realized that it's not correct, he kind of was very fond of it. But my point is what I'm saying up in the top right corner is that just because your hypothesis is nice and you have a nice idea, it doesn't mean it has to be true. So beauty is not equal to truth. Okay, but of course then, because of this great mathematical achievement and idea with the Platonic solids, he got the chance to work with Tycho Brahe, the great astronomer who for something like 2 decades collected astronomical data. So basically astronomical observations without using a telescope. But so without using a telescope, he was able to collect astronomical data that were correct to 2 arc minutes. So 2 arc minutes is 1/30th of a degree. And if you know that how tiny a degree is, 1/30th of that is a great accuracy. So Tycho Brahe had the best data in the early 17th century, and Kepler inherited all this data, and from it he was able to come up with these 3 laws of planetary motion. So the first 2 laws he published in Astronomia Nova in 1609, and the third law he published in Harmonicas Mundi in 1619. So the first law, I'm sure you have all heard about these these laws of planetary motion, but let me just quickly go through them. So the first law tells you that the orbit of a planet is an ellipse. It's not a circle as ancient Greeks imagined and people up until Kepler imagined them to be. They always wanted to use circles and circles going along circles. So people were very keen on the idea that it has to be circles. Circles has to be used when you are drawing the planetary orbits. But in fact, Kepler, almost by accident, realized that the orbit of Mars is best modeled by an ellipse. So he was actually looking at Mars, but here on the image I have the Sun and Earth. Of course, it's not to scale at all, but the point is that the planet moves along an ellipse, which has two focus points, and in one of the focus points we have the Sun. Okay, so that's the first law. The second law is the area law, Kepler's second law, which says that if you connect the planet to the Sun, to the center, to that focus point, this line segment will sweep out these sectors, and let's say in each month it sweeps out one of these yellow sectors. And the point is of this law that in equal times it always sweeps out equal areas. Okay, so let's say in each month it sweeps out the same area, that line segment connecting the Sun and to the planet. Okay, and that tells you something about the speed of the planet, because in order, so since the ellipse is sort of an oval shape, it means that when it's further away from the Sun, the planet, further away from the Sun, it has to move slower because we have these long, skinny leg of the sector. So this arc, the orbit, has to have a short arc on the far side of the Sun in order to have the same area. When it's close to the Sun, it has these tiny short legs, so it has to speed up and cover a lot of distance in the same time in order to have the same area for this sector. Okay, so that's the second law. And the third law is about the orbital period, is the time that it takes the planet to go around the Sun. So it says that the square of this orbital period is directly proportional to the semi-major axis of the ellipse, and that is the longest axis, the longest sort of the width of the ellipse. Okay, so it says that if you take the major axis or the semi-major axis and you take its cube divided by the orbital period squared, you will get a constant. And in fact, Kepler claimed that all of these ratios for any planets is always the same constant. Okay, so these are the three laws, and now with these laws we can start looking into the behavior of planets. Let me go back to item pool. So I ask you to go to item pool now and try and answer the next question. So which asks you about a year in Venus. So how long is a Venusian year compared to an Earth year is the question. Of course, we have three possibilities. A year on Venus could be longer than a year on Earth, or it could take the same amount of time. These orbital periods could be the same, or perhaps a year on Venus is less than a year on Earth. So it's a simple question. I have even given you a hint in the form of Kepler's third law and in the form of this image right here. So on this image you can see the Sun, and in front of the Sun, I don't know if you can see that small black sort of speck, that's Venus. So this is a photo taken from Earth, of course, about the Venus transit. So I'm curious to see if you understood Kepler's laws. You should be able to answer this one correctly. So as always, let me just put this in the chat. So you can go to itempool.com // Kepler/live and submit your answer on this website, and I will reveal what you have voted for in a minute or two. Okay, so I already see something like 15 submissions, which is good. My computer tells me that there are something like 42 of you, which is the greatest number of viewers ever. But so if you are watching and you haven't voted yet, go to itempool.com/Kepler/live, open it on a separate tab, and vote for your answer. I would be curious to see if it seems like most people voted for the same thing. So either all of these 15 people got it wrong, or it's good that we have a big majority of people getting it right. So there's a question by VK. What did I say about the orbital period? So the orbital period is the time it takes the planet to go around the sun. So that's basically how you would define a year on your planet, right? So a year on Earth is the time it takes for us to go around the sun once. Okay, so I'm going to, I think most of you who have wanted could vote, but don't worry if you didn't get to vote, there will be plenty of other opportunities. Let me just finish this poll and reveal the answer. So it was option C, of course. So a Venusian year is shorter than an Earth year. So, and this is something I actually can show you. So all you have to do is just take Kepler's third law and notice that if you want to get the same ratio of semi-major axis cubed over orbital period squared, all you have to notice is that Venus is closer to the Sun. So the semi-major axis, the numerator is going to be a smaller number for Venus. So in order to get the same fraction, you want the denominator, the orbital period, to be smaller, to be less as well, right? So that is all it took to answer this this question. But let me just do a short calculation for you. So here is a notepad in which I will be calculating the Venusian year for you. So we have the semi-major axis of Earth. I set it to 1 astronomical unit. So if you don't know what an astronomical unit is, it's just the distance of Earth from the Sun, sort of an average distance. It's something like 150 million kilometers. So let me set it to 1 astronomical unit. For Venus, the same number is something like 0.7 astronomical units. For Earth, of course, 1 Earth year in Earth years is 1. Here is that same equation that appeared in Kepler's third law, rearranged. So I did rearranged it to express the orbital period of Venus using the other three numbers. So in fact, since I'm working in astronomical units and Earth years, these two numbers, T Earth and A Earth, they are nothing but 1. So all we are doing is we are taking this number 0.7, raising it to the third power and taking its square root. So what we get is this number, 0.615, and this is in Earth years. So let me multiply that number by 365.25. So that's the number of days in a year on Earth, and here's the number that we get. So in fact, a year on Venus takes about 224 Earth days. Okay, so if you look this up, this is actually very close to the actual number of days it takes for Venus to go around. Number of Earth days it takes for Venus to go around the Sun. Okay, so all right, let me then move on from Kepler's laws. Now we have seen these 3 laws. We have understood them. Now I have to say that these are great. Kepler's laws were a great achievement of Kepler, but they are empirical, so they come from experience, from the measurements of Tycho Brahe, so they do not explain the cause of the motion of the planets. And in fact, for like a good 50 years in the 17th century, it was a great question. It was a challenge for the thinkers, the scientists of 17th century, to figure out questions like, what is it that keeps the planets on their orbits? What could be the source of this force? Well, here is an image of a 14th century illustration from a codex, in which you see these celestial spheres being rotated by angels who are turning handles. So people suspected that this is not the correct picture, the correct cause of motion. So they suspected that it has to do with the sun, but the correct form of this attraction by the sun wasn't clear until sort of the second half of the 17th century. And the way people like Newton derived this correct form of the gravitational force was actually using Kepler's laws. So here is Newton's great work, one of the greatest scientific publications of all time. It's Newton's Principia from 1687. So this was his great work, in which among other things he derived Kepler's laws of planetary motion using his second law, the law of dynamics, F equals ma, and the universal law of gravitation, that gravity weakens sort of with the square of the distance. It's inversely proportional to the square of the distance from the sun. Okay, so let me go over to my notepad and try to show you a derivation of Newton's gravity using Kepler's laws. Okay, so first we have to imagine that we have this circular orbit. So here is the center, here is a circular orbit, and we have to imagine a planet moving around in a circle. So what we have is, well, the circle has some radius, and the object moving along this circle has a certain speed. Okay, so that's the speed. This is the radius of the circle, and of course, at some later point, if it stays on the circle, it gets to some other point, and it will have sort of the same speed. Well, we'll see why is it that it will have the same speed. It has to do with Kepler's laws, but basically this is still the radius, this is the angle that changed. Let me call it delta theta, let's say. So what happened here is we had this object moving around the circle, and we have these velocity vectors drawn. So the point is that it moved from this point to that point on the circle. So it had changed its position by sort of delta r, okay? And its speed has also changed, well, in the sense that this vector, that was the velocity vector, got rotated. Okay, so this, well, this right here is delta v. And the main observation here is that this angle is the same angle that we had right there. It's delta theta. So if we now write down, so what I'm claiming is that these two triangles are similar. So since they have the same sort of, they are both an isosceles triangle with the same angle at the apex, what we have here is delta v over v. So the base of this triangle and one of the legs has the ratio which is the same as the same ratio of quantities in this triangle, so that's delta r over r. Okay, so if you have this, you can do the following. You can look at divide by the time it took for this motion to happen. So what you will get, and maybe multiply by v, what you will get is delta v over delta t is equal to v over r. So I multiplied by v, and I have delta r over delta t. So if this time interval gets shorter and shorter, this relation stays valid, and when delta t goes to sort of 0, what we are getting here on the left hand side is actually the acceleration, the centripetal acceleration of our body, of this body moving. And what we are getting on the right hand side is the speed squared over r, because delta r over delta t also tends to some quantity, and it's the rate, it's the distance over the time, so that tends to the speed. So that's why we have v times v over r when delta t gets shorter and shorter. Okay, so all we have here is we just derived the formula for the centripetal acceleration. So let me just write down Newton's F equals ma. So we are looking for the force acting on this object, keeping it on its circular orbit. So that's F equals ma, where a is the centripetal acceleration. So that we just noticed to be v squared over r. So we have m times v squared over r. Okay, now what is v exactly? Well, just think about this. So according to Kepler's second law now, so we will be using Kepler's laws. Right here we have to use Kepler's second law, because what it says is that in equal times it covers equal areas. This line segment sweeps out equal areas in equal times, and when we are talking about a circle, that means that the speed must be constant. Okay, so Kepler's second law, let me just write Kepler 2. So Kepler's second law says that v is constant, and it has to be equal to the circumference of the circle divided by the orbital period. So the circumference of the circle is 2 pi r, and it has to be divided by the orbital period. So why did I write this? So all I did was looked at Kepler's second law, so that the speed must be constant. So the speed is of course displacement over time, so this distance over time. So I took one full orbit, so that's that distance is the circumference of the circle, and the time it takes to do that one full orbit is capital T, is our orbital period. So this is the formula I got for v. Now I can square this and write the following. So if I square v, I get m times 4 pi squared times r squared over r times t squared. Okay, so this is what I got for the force. Now I can apply Kepler's third law. Okay, so Kepler's third law, which says that the distance cubed divided by the orbital period squared should give me the same constant. Let's call this constant capital K. And if I use that, I can write t squared as r cubed over k. So this t squared over there can be replaced by r cubed over k. So that gives me a multiple of k, well, a factor of k times m times 4 pi squared. Then I have r squared upstairs, and I have r times r cubed. Okay, so this is what I got by applying Kepler's third law. So if I simplify by r squared, you see that I got for f the following. I got that it's 4 pi squared k times m over r squared. So this is the inverse square law. This is Newton's gravity for the special case of a circular orbit. And you might be asking, where did I use Kepler's first law? So here I applied Kepler's second law, here I applied Kepler's third law. Where did I apply Kepler's first law? Well, I applied it in the sense that I took a special ellipse, that is the circle, for the orbit of my very special planet. Okay, so applying Kepler's laws can lead you to Newton's gravity, the inverse square law, in the very special case of circular orbits. And sort of Newton's great achievement and great idea was to take this form of inverse square law and apply it to not just circular orbits, but basically all planets and all objects which has mass. Okay, so this is why it's called the universal law of gravity. Now, let me go back to the slides now and show you, show you something that I wanted to say. So previously, that several people knew, of course, that this is the correct form of gravitation, of the gravitational force. So including Robert Hooke, people knew that it's probably an inverse square law, but the actual first proper mathematical treatment was given by Newton. Okay, so this is why it's his big achievement. Okay, so maybe it's time for me to tell you what's going to be included in this talk and what won't be included in this talk. So we've already seen Kepler's great idea. This is called the Mysterium Cosmographicum. It was a great idea, but alas, it was wrong. Then just now we've seen how Kepler's laws can be used to derive Newton's law of universal gravitation. Now the next task, and this is basically our main objective for this lecture, is to go the other way, use Newton's law of universal gravitation and derive Kepler's laws. So this is how science progresses. You take some things like Kepler's laws. These are empirical, observational laws. You deduce something from it, like Newton's law of gravity. You generalize it. You say that perhaps it applies not just to circular orbits, but to elliptical orbits as well. And then you show, you prove that indeed this generalized, in this generalized setting, the universe, the law of gravity still holds, because it gives rise to the Kepler ellipses. Okay, and maybe much more, and in fact that is the case. Okay, so this is the main purpose of this talk. We will see during this derivation that sort of the main idea, the main thing that we'll use is conserved physical quantities. So physical quantities that do not change in time. And you will see through this derivation how useful these conserved quantities can be. And then I'll finish off by discussing some of the effects of the Kepler's laws, the effects they had on other areas of science, and there will be a surprise at the end. So what is not going to be in this talk is differential equations. So usually what people do, so when you go to university, and let's say if you study physics, if you decide to go and study physics at university, you might see a derivation of Kepler's laws from the law of gravity. But that derivation, well, the way usually teachers present it is by solving something called the differential equation. And it involves some tricky substitutions, and it's not at all clear how you can think of such a derivation. And I think sometimes it might be even more complicated than it should be. So what I also won't have in this lecture is alternative derivations. So there are many ways to derive Kepler's laws. I'm only going to show you one way, but I will mention a few of these other ways of proving Kepler's laws. And of course, lots of historical details. So I'm not going to be able to tell you the whole story. It's a fascinating story. There are lots to learn, and I will give you some references, including this book by Arthur Koestler. So it's called The Sleepwalkers, and if you are looking for a good read about Kepler and Tycho Brahe, Galileo, it has it all. So it's a really good book written in a nice way about these scientists kind of sleepwalking into discovery sometimes. it's a really good read. I can recommend it. Okay, so let's see. Are there any questions? Yes. So at the moment, so VK asks. So the equation I derived is limited to circular orbits, and yes, that is the point. So at the moment, what we have seen is that the law of gravity is connected to circular orbits. It might be just to be restricted to that motion, but it will turn out that it in fact is not the case. Yes. Okay. So do ask questions if you have any. I'll try to answer them. Okay. So of course there is this word in the title, elementary, and I should explain what I mean by elementary. And I have found this this quote by Richard Feynman, who actually gave a similar lecture on the motion of the planets around the sun in the 60s, and he said that his derivation will be also elementary, but elementary does not mean it's easy to understand. Elementary means that very little is required to know ahead of time in order to understand it, except to have an infinite amount of intelligence. So this is typical Feynman, half jokingly saying that elementary means that each step is easy to understand. Well, each step is kind of easy to follow, and you are starting from something that is not that much. Okay, and in the end you will see this nice structure of your argument resulting in Kepler's laws in this case. Okay, hopefully. So what are we going to use for these things? Well, I will be using arithmetic operations, so addition, multiplication, division, so all of that stuff that people learn in primary school. Then I will be using basic geometry, so this is secondary school stuff, I would say, all to do with scalar products and vector products of vectors. So I'm assuming that you all know what the dot and cross products of vectors are and what properties they have, but I will be referring to these properties. So even if you don't know these properties, you just have to accept or believe what I say. But after the lecture, you can check that these things are indeed true. I'm not going to prove things related to these two operations, but I'm going to use them. So this is something that I would say is elementary at this point. And I will also be using a tiny bit of calculus. So I'm not going to solve differential equations and use that big machinery of analysis, but I'm going to use a tiny bit of calculus, which might be something that appears in further maths. I'm not sure, but it is definitely something that you would see in the first year of university, and that is how these products, the scalar and vector products, behave when you take the rate of change of these products. And there are these very simple rules that the way you take the way you differentiate, the way you take the rate of change of a scalar product is you take the rate of change of the first vector and the dot product of that with the second vector plus the first vector as the first vector's dot product with the second vector's rate of change, and the same goes for the vector product. So you take the first vector, take its rate of change, and then you rest for a bit, and then you take the second vector and its rate of change. Okay, so it's called the product rule, or sometimes it's referred to as Leibniz, the Leibniz rule. The way my teachers taught me at I think university is that you start differentiating, you get tired, so you don't do the whole thing. you just first differentiate the first factor, and then you add to that another term where you have differentiated the second factor after you rested for a bit, and it's the same for the vector product as well. So this is all I'm going to use basically. And if it seems easy for you, then mission accomplished. Then I proved my point. My point being that this derivation should be elementary. Okay. All right. Now let's see. So of course, over the years, as I mentioned, just quickly I want to go through this. So over the years, Kepler's laws have been derived in many ways. And a few examples are, of course, Newton, who was the first one to derive Kepler's laws. He used geometry and his calculus that he just developed to derive these laws from his universal law of gravity. Then there was Jakob Hermann and Johann Bernoulli in the early 18th century, who used polar coordinates and solved the differential equation. So this is actually the kind of derivation that people see at university usually. Then there was Laplace, the great French mathematician at the late 18th century. Had a different approach where he used these conserved quantities that I'm going to show you, but he also solved the differential equation. So after all, this was a bit more complicated than the thing I want to show you. And then there was a whole list of people doing the same kind of derivation in slightly different ways, but sort of the core idea for all of these people in the 90s and the 20th century, so Möbius, Hamilton, Maxwell, and Feynman, they all used this this notion of a hodograph, which is just the shape, the curve that is traced by the velocity vector. Okay, so we are not going to approach this in this way, but I just wanted to tell you about these different ways of deriving Kepler's laws. Okay, and for the last derivation is by two Dutch mathematicians, Van Handel and Heckman, from 2019, and this is the derivation that I'm going to follow, and I will give you a reference to this paper if you want to read Van Handel's and Heckman's paper. There will be a reference at the end of the slides. Okay, so this is the geometry plus conserved quantities type of derivation that I'm going to show you. Okay, so let me move on to the two-body problem. So because the sort of the Kepler laws talk about a planet orbiting the sun, I will start with the two-body problem, where we imagine the Earth and the sun gravitationally attracting each other, you know, with the same magnitude of force, but being, you know, pointing in opposite directions. So this is Newton's third law, of course. So imagine the two objects, the two point particles with masses m1 and m2 placed at positions of r1 and r2 in 3D space, and connect these two points, and let's introduce a new vector called r, which points from m2 to m1. So this is just the difference of these two vectors. It's pointing from the sun to the Earth at the moment. Okay, so this is r, and then we can express the force acting on m1 as minus capital G, that's the gravitational constant, times m1 times m2 over r squared. So r here is the distance between the Earth and the sun. So this is Newton's universal law of gravitation, Newton's law of universal gravitation. So we have the gravitational constant, the product of the masses, and dividing that is the distance squared. So the last thing we have here is this vector r connecting the two bodies divided by its own length. So if you see these letters without the arrows on top, those refer to the length of that vector. Okay, so r here denotes the length of my vector little r. Okay, so this is the distance between the 2 points, and here I'm dividing r by its own length, making it shorter by making it of unit length. So it's just normalizing the vector. So f here has this minus sign because, as I said, the vector r points from m1, m2 to m1, and f, as you can see here, this blue arrow, this force is pointing from Earth to Sun. That's the attraction of the Sun on Earth. Okay. Now the next thing I want to do is fix the origin in the center of mass. So what do I mean by that? So these two massive bodies have a center of mass, which is actually somewhere inside of the Sun, but let's just say it has to be somewhere along this line, okay, the center of mass. And what I'm assuming, or what I'm asking us to do, is to fix the origin of our coordinate system along that line in the center of mass. That basically means that if I take the center of mass, which is just m1 times r1 plus m2 times r2 divided by the total mass, that should be equal to the zero vector, sort of the origin of my coordinate system. So I didn't divide this by m1 plus m2 because I can just always multiply both sides by the sum of the masses. So this is just my choice, special choice of a coordinate system. So if I have this specially choose coordinate system, I can express these two vectors r1 and r2 using this vector little r. Okay, so my point is that I have this line segment connecting the two masses. I put my origin put the origin in the center of mass, so r1 and r2 can be expressed by using this vector r pointing from m2 to m1 and just basically correctly scaling them, rescaling little r gives me r1 and r2. And you can see that in fact r1 pointing from the center of mass to the Earth should be a positive number times the vector r, and r2 from the center of mass to the Sun should be a negative multiple, some negative number multiplying little r. Okay, so you can use the first equation and the third equation to express r1 and r2 via this little r vector. And if you do that, in fact, you can express the total energy of this system of two masses gravitationally attracted to each other in a simpler way. So basically what I have here is the kinetic energy of m1 written as 1/2 times the mass times the velocity squared, plus the kinetic energy of the second body, the Sun, written as 1/2 times its mass times the velocity squared. And then I have the potential energy, basically the term that comes from the gravitational attraction. So this is minus capital G times m1 times m2 over distance, divided by the distance. Okay? And the point is that since I was able to express r1 and r2 via this little r, I can express these velocities or these speeds using the speed of this vector coming from this vector little r. So let me just try to show you how I do that. So I'll switch to my notepad, and so what I'm showing you here is the previous formulas expressing R1 and R2 using the vector little r and sort of some combination of the masses, and that means that the speeds should also have the same relation. Okay, so this right here is actually v, sort of the speed of this vector r. Okay, so now we have these relations, and what I want us to compute is the kinetic energy. So it's 1/2 times m1 times v1 squared plus 1/2 times m2 times v2 squared. Now if I take these, well, and there is of course the gravitational potential minus capital G times the product of the masses divided by the distance between the two objects. So now I can substitute for v1 and v2 these expressions on the right hand side of each of these relations, and what I will get is 1/2 times m1 times m2 squared divided by m1 plus m2 squared v squared. Okay, so this is just v1 squared plus 1/2 times m2 times m1 squared, because I'm squaring the right hand side of this inequality, of this equality. So m1 squared plus m1 plus m2 squared times v squared, and then of course I have to subtract the gravitational, so that's g, gravitational potential. But the point here is now we have this combination of masses. So if I write 1/2 times m1 times m2 divided by m1 plus m2, okay, times v squared. So if I collect these common factors from these terms, so 1/2 is a common factor, m1 times m2 is a common factor, and also m1 plus m2 in the denominator is a common factor. What I'm left with in the first term, what remains is m2 divided by m1 plus m2, and in the second term what remains is m1 divided by m1 plus m2, right? So I hope that's clear. So I collected these common factors from the first two terms, and what I'm left with is this combination of the masses. But if you look at this carefully, these are two fractions with the common denominator. So it has m1 plus m2 in the denominator, and what it has in the numerator is also m1 plus m2. So this right here is equal to 1. Okay, of course I have to remind myself to include the gravitational potential, the potential energy, and so this is something I've been just carrying with me. So now I have the following expression for the total energy. It's 1/2 times mv squared minus k over r, where I introduced these two new quantities, m and k. M is equal to this thing right here, m1 times m2 divided by m1 plus m2, and k stands for this numerator, so that's g, gravitational constant, times the two masses. Okay, so this is what I end up with. So these are some newly introduced quantities. M right here So I can go back now to the slide. m1 times m2 over m1 plus m2 is something called the reduced mass, and this constant k is just proportional to the gravitational constant. So what you have seen here is that the total energy of these two bodies being attracted to each other gravitationally can be expressed as the kinetic energy and the sum of the kinetic energy and the potential energy of something that looks like a single object, right? So if you look at the kinetic energy term right here, it's just 1/2 times m times v squared. So it looks like the usual kinetic energy of expression for a single object. So the point is that you can replace effectively these two bodies by a single object having this mass of m1 times m2 over n1 plus m2. It's called the reduced mass, and with this sort of constant giving you the strength of this gravitational attraction. But in this rewriting of the two-body system as a one-body problem, now we have this one body with mass little m being attracted to the origin. Okay, so this might have been a bit, I'm not sure if it was completely clear. I hope it was. Let me move to item pool and ask something that might show us if you got this about the reduced mass. I have a question. Let's see if this works. So my computer is a bit slow. I just want to go to the next question. Here it is. So go to itempool.com/Kepler/live and answer this question. Okay, let me just put this in the chat. So the question is, first of all, I'm telling you that the Sun is roughly 1,000 times more massive than Jupiter. Jupiter is the heaviest of the planets in the solar system, and yet it's only 1,000th of the mass of the Sun. My question is, what is the reduced mass of the Sun-Jupiter two-body system? So I even put here the reduced mass. So it's the mass of the Sun times the mass of the Jupiter divided by the mass of the Sun plus the mass of the Jupiter, and I want you to express this in terms of the mass of Jupiter. So all I want you to do is to go to itempool.com/Kepler/live and enter a number that you calculate by using this fact that the Sun is 1,000 Jupiter masses. Okay, so if you rewrite this reduced mass so that m Sun, the mass of the Sun is replaced by 1,000 times the mass of Jupiter, you will get a single number in front of m Jupiter. Okay, so I hope this makes sense. Let me just look at the chat. So you can input it in any way you'd like. I believe if you tap on to or click on this input box, a virtual keyboard should come up where you can input mathematical expressions like fractions. But if you input decimal expressions to I don't know how many, probably a couple of decimal places, I think it should be accepted by the system. We'll see. But I think there should be the option of writing it as a fraction. Okay, in the meantime, let me just look at the chat. So yes, reality -3 says that m1 times m1 times r1 plus m1 times r2 equals 0. Looks like moments. Yes, I guess. And Luca M says, unfortunately, that procedure of reducing the number of bodies by 1 is not easy for more than 2 bodies. In fact, that is true. So this reduction of the 2-body system to 1-body motion is it gets much more complicated when you have more than 2 bodies to begin with. Okay, so I already see 8 people have submitted their answer. I will give you another minute and then I'll reveal the correct number. Okay, so let's that probably gave enough time for everyone to. Okay, there's a new submission. So do let me know if you need any more time. So there's a question: how do you derive the gravitational force equation? You mean the form of the inverse square law? So I did that using Kepler's laws, but in the end you have to start from something, right? Right now what I'm claiming is that we try to go the opposite way. We, instead of starting from Kepler's laws and getting to the the law of universal gravitation, we are going the other way. We are assuming we have this law of gravity, and we are trying to get as much out of it as possible. If it works the other way around as well, if we can derive Kepler's laws in the end, that means that we replaced these 3 laws of planetary motion by just one single law of gravity. So we got a new yes. So basically, in this case now, the way we are progressing, it's just assumed. It is just something that we start with and see what we can get out of it. If we can get to the Kepler's laws, that means that we can just replace Kepler's laws by a simpler, a somewhat, well, definitely something that is only one thing instead of 3. So, and this is basically, well, this is I think a very nice example of scientific progress, because instead of having 3 things to keep in mind, Kepler's laws, you only have one thing, this form of the law of gravity, to keep in mind. So that's progress, I would say. And in fact, there are much more to be gained, obtained from Newton's gravity. Okay, so let me just close this poll. So the correct answer was 1000 over 1001. So yes, some people try to input something that's similar, probably not to enough decimal places, so that's fine. But the main point is that this reduced mass is really close to being one Jupiter mass. Okay, so if you have 2 objects, one of them is really heavy compared to the other one, like the Sun compared to Jupiter, the heaviest object, the heaviest planet and object in the solar system other than the Sun, you are getting something that is, when you reduce the 2-body problem to the 1-body problem, the reduced mass that is in that one body problem is almost the same as the mass of Jupiter. Okay, so that's my point with this